So we're just going to review the events of an action potential. Okay. Okay, so just to start off here, we have our graph. We have time on the x, and let's put the membrane potential change on the y. Okay, so right off the back, we've differentiated 2 points here. Can anyone tell me what those 2 points are, what those 2 membrane potentials are? The numbers, and then they are. All right, so this would be -70, correct? -70 millivolts here. And what would that be in terms of a description? That's not potassium, that is not threshold. What did we call -70? That was what's happening at rest, right? That's your resting membrane potential. Right? And then we also mentioned threshold, which is what value? -55. So -55 millivolts is our threshold value. Okay. And just to be clear here, this is a representation of the change in the membrane potential over time with regards to the events of an action potential. So there are 3 general regions or 3 general areas of the action potential here. That'll be your first area. Okay, so let's sort of describe what's happening in each of these phases. So the first phase we know to be depolarization. We'll talk about what happens here first. So what is happening in depolarization? So we're starting at rest. Our membrane potential is -70 millivolts, which is representing an increased permeability of which ion? Which ion is more permeable at that stage? The membrane is more permeable to which ion at rest? We spoke about this. Yes. Potassium, perfect. This is why we start this negative, right? -70. It's much closer to the equilibrium potential of that ion of potassium. Okay. Now, as you begin to depolarize, what happens? How does the membrane potential change? What are the first events of the action potential after we've gotten to threshold? The voltage-gated sodium channels open, and so we have an increase permeability. I'll write permeability as this large P, so an increased permeability to sodium, right? And that means that the voltage-gated sodium channels have opened. Now we know these channels have 2 gates on them. So which of these gates are open and which are closed? Which of these gates are opened and which are closed here? Or are they both open or are they both closed? So what is the state of the gates, both the activation and the inactivation gate on the voltage-gated calcium channel after we have depolarized the threshold? Come on, we talked about this. So, okay, so that's correct at rest. So at rest, the inactivation gate is open, but the activation gate is closed, and so it's capable of being opened, right? Then we open the activation gate after threshold, right? So after threshold, both gates are open. Okay, can we see that? So what's happening here is both gates are open, right, during depolarization. what we just described was what was happening at rest. Okay, so essentially, we increase our membrane permeability to sodium, which means both activation and the inactivation gates are opened. Right, this is how we get ion movement here, rapid ion movement, which is changing the membrane potential here, making it much more positive, and that is what happens during depolarization. What about the membrane permeability to potassium at this point? What's happening in this phase to the membrane permeability of potassium? So we know at rest, there's an increased permeability to potassium. Is it? It's decreased, so it's slightly decreased. So during depolarization, we have an increased permeability to sodium and a decreased permeability to potassium, which simply means that the voltage-gated potassium channels are closed. Okay. And so essentially what's happening here is that the membrane potential approaches the equilibrium potential of sodium, right? And all that means is that it becomes more positive. Okay, the membrane potential is rising and it's approaching the equilibrium potential of sodium, which is a lot more positive than rest. And so the membrane potential becomes, can we see that? So this is just a large E and then subscript sodium. All right. So that's depolarization. And the membrane potential there becomes more positive. That's like the upshoot or the upstroke of the action potential. What is the maximum value that the membrane potential gets to? It doesn't actually get to the equilibrium potential of sodium. What does it get to? What's this peak value? Positive 30, perfect. Positive 30, I thought you said positive. All right, so this is your positive 30 millivolts, and that's as far as we get before repolarization. Now, what's taking place during repolarization? What is taking place in terms of the membrane potential and channels during this second phase of the action potential?
Our sodium channels are opening and then potassium channels are closing, and then sodium channels are closing. Potassium channels are opening.
Good. So we decrease our membrane permeability to sodium here. All right, we'll talk about the gates for that in a minute. And then we increase our membrane permeability to potassium. All right, now during repolarization, what do we have closing? Which of the gates are closed? Which of the gates are closed during repolarization? It's not the activation gate, the inactivation gate. All right, remember, if the inactivation gate is closed, there can be no ion movement. So what we have is the inactivation gates close. But the activation gate is open. And although the activation gate is open, as long as the inactivation gate is closed, there is no ion movement. All right, so essentially, this channel is closed. What about potassium? We have opening of the voltage-gated potassium channels. What does this do? What does this do to the membrane potential? If we close sodium and open potassium, what are we doing? Come on. Making it more negative again. Making it more negative again. Perfect. So here, the membrane potential. Becomes more negative. Okay. All right, and then the last phase here, a very brief phase, is called hyperpolarization. Hyperpolarization. Okay. And what's happening during hyperpolarization? What is happening during this phase? So this is like the overshoot phase. We're attempting to get back to rest, and then we overshoot the membrane potential. We get really negative, about negative 84 or so. So what's happening here?
Is hyperpolarization is getting closer to the negative 94.
Right, so it's getting closer to potassium's equilibrium potential. That's correct. So what we're doing is we have an increased permeability to potassium here, and that is because the potassium channels are in the process of closing. They're not closed just yet. They're in the process of closing. So those voltage-gated potassium channels are in the process of closing. Okay. And what's happening with sodium? What's going on with sodium? So we know potassium channels are closing. Not yet, no. So we have a decrease in the permeability of sodium again. Yeah. Let's talk about the gates. Is the inactivation gate now closed or open? When we get back to rest, is it possible to fire another action potential here?
Yes.
When we get back to rest?
Yes.
It is, right? So after we get back to negative 70, our activation gates are closed, but they're possible to open. So the activation gates are closed, but the inactivation gates are open. And so during this phase, when we get back to rest here, at the end of hyperpolarization, we're leaving the refractory period. The inactivation gates are now open again, and there is the possibility of depolarizing to threshold.